Welcome back. Today we're going to discuss more timers. The only timer instruction that we've used so far, and we demonstrated it in the garage door application, was the on delay timer. In on delay timer, you have to go back to the days when they had mechanical timers. Now these were things that looked like big relays that plugged into an octal socket. That means it was like a vacuum tube socket that has 8 pins, and it plugged in there. It looked like a relay. It probably had a knob on top, maybe with some gradations for adjusting the time delay, and it was mechanical. And it used a dash pot, which is basically you release something and a spring pressure pushes on a diaphragm, and as the air leaves, that's your delay, and then the contact closes. So originally, when you bought a timer, it was a piece of hardware. Originally it was mechanical, and it basically had a motor, maybe, that when you energized it, the motor ran and then it closed or opened contact. So there was a delay between you initializing the timer device and then some change in state. Now, most of them, when you initialized it, there was something that would happen right away. A contact would open or close, then after delay, then something else would happen. So this evolved into the timers that are in controllers now. And when you're working with timers, you're counting units of time. And you have 3 periods: before you started it, while the timer's accumulating, and after the timer's done. Then you could also say after the timer's done, but it's not reset yet. So all these instructions are all giving you ways to work with those different periods of time involved with time, before, after, during, etc. Now the Micro 800 has more timer instructions than the MicroLogic Slick 500 family, and more than RS Logix 5000. With RS Logix, and by that I mean 500 Micro Starter, which is a stripped down version of RS Logix 500, and RS Logix 5000, you basically had a TON, a TOF, and an RTO. On delay, off delay, and retentive on delay. With those instructions, you had something called a timer timing bit. That bit would be high anytime the timer was timing or accumulating. So you could use that as a pulse. If you had an on delay timer set for 1 second, you initialize it, it starts accumulating, the timer timing bit is on for 1 second. Then the done bit comes on. Okay? With the Micro 800, they give you other timer instructions, so you don't use the TON for as many applications. Now we're not going to cover them all. So let's get into the lab M7 more timers. In the lab project manual, we told you to create a new project and name it TON TOF 01, and that we would be using the LC10 or the Micro 810 for this project, and which we did when we wrote the manual. However, we're using the simulator in all of the lab projects in this video series for this course. The alternate was to take and delete all the logic from after you save your garage door, then rename it, and then delete all the logic, and then we had to go in and edit and change some of the aliases associated with input 0, output 0, and output 1. I'm not going to do that. I'm going to create a brand new project from scratch just to mix it up a little bit. You already know how to do the rest of it. New M7 TON TOF. Select a controller, Micro 850, Sim. Add to project. First thing we had you do, you have to have a program, and we're going to make it a ladder logic diagram program, and we're going to name it TON TOF. Open the program and add a rung of logic. We had a true-if on. We used input 0. Now I can select input 0 from here, or I could have canceled the pop-up and just typed in input 0. Now input 0 in the garage door project was IN00. Remember, this is a brand new project, so I'm using the direct I/O. This is not buffered I/O. That's why I said I'm going to mix it up a little bit just to give you something slightly different. Then I had you pull in a TON. I can get the TON from up here, but just to give you a little exercise on the toolbox, I'm going to select the toolbox. I'm going to grab an instruction block and drop it in here, and it comes up what type of instruction block. Now, before we typed in TON, I'm just going to scroll down to the T's. Right there's the TON. Double click on it, and there it is, TON1. Now I'm going to add a direct coil, drop it in there, and we're going to use output 0. So we go to the I/O, back up to the top, output 0. And this is the rung of logic that we had in the manual, except this was IN00 and this was OUT00, and it has some names on it. I also had you put in a preset of 2 seconds. Now, I tend to use thousandths of a second, so T # 2000 milliseconds. Then I had you save this. We already have a name, M7 TON TOF. Save it and download. And of course, we can't download because we don't have our simulator running. Remember, this is a new project, so we have no path. See, there's no connection path. And that's one reason for mixing it up a little bit like this, is so you don't get used to having everything already set and you have to redo some of the things that you've already learned. So the first thing I have to do, I can't connect unless I have a controller to connect to. So I'm going to start the simulator. And of course, this is the correct IP address. I'm going to power it up and then drop it down below out of the way. Now I'm going to go over here to connection path. I'm going to drag this out. We need a little bit more space. I'm going to hit the edit, set up connection path. I'm going to select it, double click on it to get it down here, and then close. We can download. I'm going to move this back out of the way, download. Just for grins, I'm going to open up the local variables and expand the timer data type, the TON1, so you can see the variables. I'm going to collapse alias a little bit so you can see the logical values better. Now I'm going to turn on input 0, watch the time accumulate here, and after 2 seconds it turns on output 0. You can see output 0 down here turned on. Turn output 0 off and you can see that the ET resets. Now save and go offline. It's not necessary to save, but by habit I save and then go offline. And then I had you add some more logic. Drop down a branch around, pull the OTE or the direct coil inside, down to our branch around, a true if off, and we don't have to go back to favorites. We can go to bit and grab a true if off, and we want that to be the Q bit for TON1, and drop down a direct coil, and the direct coil is going to be output 1. So we go to the IO micro 850 and we pick the next output. Now we still have something here. We need to add the done bit, if you want to call it that, Q from TON underscore 1. So we go up and type in TON dot Q, and there's our logic. Now I had you save and download this. We're going to operate this timer. I want you to watch the relationship between digital output 0 and digital output 1. It's just as easy to watch it here in ladder logic as it is down here on the simulator. I'm going to turn on input 0, and you see that the not done is on right away, then the done comes on. Or rather, I should say, output 1 goes on immediately when it's enabled, stays on for 2 seconds, and then goes off, and then output 0 comes on. So you could say that output 1, digital output 01, right down here, gives you a 2-second pulse. And you could use this logic right here to create a pulse at whatever this bit is. Now we did it at digital output 1 just so you could see the light come on down here. Let's do that again. Turn off 0, turn it back on. See, 1 comes on, it's on for 2 seconds, goes off, and then 0 comes on. Just for grins, I went offline and put aliases on these two I/O addresses, memory addresses, done in timing. We'll exercise this again. We turn off input 0, that resets everything. We turn it back on, it starts timing, and while it's timing, this bit is on. And it's not that you have the not Q or the not done. You have to have the enable and the not done. If you got rid of this or moved it inside here, it would not behave the same. So watch it one more time. Turn off input 0, everything resets. Turn it on, the timing bit comes on for 2 seconds, off, and then the done bit. So I'm going to go offline and change this up a little bit, and I'll be right back. What I'm going to do is to move this instruction inside. So now the only condition for timing is not done, and you're going to see that the timing and the done don't behave the same as they did before. Notice now that we move this condition inside of the branch that the timing bit is on all the time now, and when I turn on input 0, nothing changes with this bit until it's done timing and the done bit comes on. So watch the done bit and the timing bit. One's on, the other's off. Then they trade places. What we're not using the enable now as part of the logic for the timing bit. That's important to make note of. Now we're going to add another rung to the program for the TOF instruction, timer off delay. I added a second rung of logic. I used the same input to start both timers. I did give the TOF a longer preset of 4 seconds or 4,000 milliseconds, and I added a full complement of aliases. So now this says start timers, TON timing. Okay, let's operate this. Let's operate these two timers. We're going to right now notice that the done is off and the timing is off for the TON. The done is off and the timing is off for the TOF. I'm going to turn on input 0 and notice that the done bit comes on right away on the TOF, and then when the TON times out, the timer timing bit went off and the done bit went on. So compare those two right now. Both of them have an output from Q. Now I'm going to turn off input 0, and if you look at the TON, it's going to clear, but pay attention to TOF. It starts timing, and the done bit was on and the timing bit. Let's do that again. Done bit and the timing bit is on. It is timing right now during the 4 seconds. And the reason I don't care for the TOF is you turn on the enable, okay? The done bit comes on right away. Try that again. Watch the done bit right here. Well, we're going to have to let it reset. Okay, watch the done bit when I enable the timer. It comes on immediately. And it stays on indefinitely. As long as it's enabled, Q output is high, on, and not until I turn off and the run goes false, then it starts timing. Done bit's still on, and as soon as it's done timing, the done bit goes off. When it's not done, it's done, and when it is done, then it's not done. So the done bit was on, the output, comes on immediately, and stays on, but it's not done. Then if you turn it off, it's still done, but as soon as the timer's done, then it's not done. Now they're not calling it the done bit and the timer timing bit. They're just calling it Q, and then we created logic for a timer timing bit. This is primarily for the RS Logix users who may not be comfortable with this format of timer instructions. This is how you can create a timer timing bit for these two instructions. Save and go offline. And now we're going to edit the logic to make a TON behave just like the TOF. Here's our logic. we replaced the TON rung. We edited this rung, added this rung that works with this rung to give us the TOF function using a TON. Save and download. Here's our logic, and down here is our simulator. We're still using digital input 0 to start both of these timers. What you want to pay attention to is TON done, which is output 0 and output 2 TOF done. So watch those two and then watch these two, TON timing, TOF timing. Okay, we're going to start 0. The dones come on, okay, and it stays just like this. It's going to hold just like this indefinitely. Because remember, with a TOF instruction, as soon as you enable the timer instruction, the TOF output Q goes high, and it stays high until you turn off the input and the delay goes by. Now these are both set at 4 seconds now, so we can watch them work evenly. So everybody look, the done bits are on, right? Now let's turn off input 0 and see what happens with the timing bits. That's output 1 and 3. Notice they're both running and the done bits are both on. And as soon as it hits 4 seconds, everything goes off. This is an off delay timer. Now remember that this logic down here is not part of the timer. I just put that in there to give you a bit so you can see when the timer is timing. And that would be like a pulse, the length of 4 seconds. And then up here, this logic doesn't belong to the TON, neither does this logic. What we've done here is shown you how to use a TON to get the same results as a TOF. And you're probably asking, why would you go through all that trouble? Well, TOFs are more difficult to troubleshoot than TONs because they're not intuitive. Because an on-delay timer, when it's done, it's done. When it's timing, it's timing. With an off-delay timer, when it's done, it hasn't even started timing yet. And then when it's done timing, then it's no longer done. Now, they don't use the terminology done and timer timing in Connected Components Workbench for the Micro 800. So this is a holdover from RS Logic's 500 Micro Starter and RS Logic Studio 5000. That is the way their timer instructions work, not CCW. This is in here to give you a chance to exercise these two timers and see some of the behavior outside of just turning on the input and watching the output to see what it does. And it's a crossover for those of you that are avid RS Logix users to see what you're going to have to do to create the same result. Now there are 8 timer instructions for CCW, and I'm only showing you 2, TON and TOF. There are some other ones, like the TON TOF, which is a combination on delay off delay. Then there's a pulse timer, which basically would be like the timer timing bit for one of these timers. There were a group of questions in the manual. The logic is at rest and input 0 is in the off state. Compare output 0 and 2. Are they in the same state? Yes. Compare output 1 and 3. Are they in the same state? Yes. Neither logic is done nor timing, correct? The answer is yes. Then we had you flip on input 0 to the on position. Did anything change with the done or timing bits? Yes, the done bits went on. The logic is at rest and input 0 is in the on state. Remember that this is off delay logic, so nothing will occur until we turn input 0 to the off position. With it off, without changing anything, compare output 0 and 2. Are they in the same state? Yes. Output 1 and 3. Are they in the same state? Yes. Now flip on input 0. Now flip input 0 to the off position. Did anything change with the done and timing bits? Yes. The logic is not at rest and input 0 is in the off state. Compare output 0 and 2. Are they in the same state? Yes. Compare output 1 and 3. Are they in the same state? Yes. The timers are both accumulating? Yes. Now all these questions, this last group, had to be answered during the 4 seconds that these timers were timing. One more group of questions on the last page. At this point, the input 0 is back off, so the done bits and the timing bits are off. The question is, the logic is at rest and input 0 is in the off state. Now remember, it was in the off state before, but the timers were timing. When 4 seconds ran out, then it went to this state. Compare output 0 and 2. Are they the same state? Yes. Compare output 1 and output 3. Are they in the same state? Yes. Would you agree regarding the bits that we are controlling? That would be output 0, 1, and 2, 3. Would you agree regarding the bits that we are controlling that the top 2 rungs using the TON produce the same results as the bottom rung using the TOF? Yes. Last thing said about this. It's unlikely that you're going to use this logic exactly as you see it in a practical program. Remember that we created this logic specifically so you could see the relationship between the so-called timer timing out and when it is actually timing. The timing bit for both the TON and the TOF, if it's timing, you can use this logic to create a pulse of that length. Now you would not do that with a TOF. You might with a TON create a pulse using the logic of if it's enabled, not done, therefore it's timing, and then that will be a pulse of the length of the preset. From this lab project, M7, your takeaway is the comparison between the TON and the TOF, between an on delay and an off delay. And you can actually take either one of them and get something that behaves like the other. No reason to do that. Personally, I never use off delay timers except when I'm doing training. And the only reason that I use off delay timers in my classes is because, remember, there are people who write code, write programs, download it in a controller on the assembly floor at the machine builder or the process builder. They troubleshoot these systems, they get them working. The customer comes in, does a sign off on the demo that it works. They do a sign off, they tear the machine down, pack it up, ship it to the manufacturing facility, and when it gets there, millwrights and machine builders come in and reassemble it. Electricians connect all the wires back up, and then someone goes in and commissions it from the laptop, so to speak. In other words, they might ring out some I/O. In other words, they might do some preliminary tests, but primarily what they're going to do is make sure that it works as built on the shop floor back at the machine builder. So whoever wrote that program, maybe they just like TOFs, okay? I mean, there's nothing wrong with a TOF. I just don't like the idea for some of the TOF instructions that when it's not done, it's done, and then when it is done, it's not done. I just don't like that terminology. So I avoid that for the sake of the people that have to read this logic later and the people that have to maintain it. Now, don't get your britches in a bunch if you got some programs in your plant that use TOFs and you want to go in and change them to TONs. Don't do that. However, we cover a lot of things that you probably would not use when writing a program, but there's no guarantee that you won't run into it and have to interpret it and figure out what the original programmer was done in order to troubleshoot the system. Okay, so that was basically the walk away with from M7 was the comparison between a TON and a TOF. Thank you.